Hello! Today we will begin with the strange identity. 3 times 2 equals 1. How can this be true? The left hand side is clearly 6, but the right hand side is 1. How can this be true unless 6 is equal to 1? Well, that's exactly what happens in a certain context. This context is known as working modulo 5. Modulo 5, numbers are glued together when they differ by some multiple of 5. For instance, 11 and 1 differ by 10, which is a multiple of 5, so in this context, 11 and 1 are thought of as the same number. One way to visualize this is to think of a number circle instead of a number line. A circle, or a clock perhaps, with 5 numbers, 0, 1, 2, 3 and 4. 5 is then placed on top of 0, 6 is placed on top of 1, and so on. Whenever you do some arithmetic in this context, we simply remove or add 5s until we end up with one of the numbers on the circle. For instance, for 17, we remove 3 5s and get 2, so we write 17 equals 2. For 4 plus 3 we get 7, so we remove 1 5 and get 2. So 3 plus 4 equals 2. 3 times 2 is 6, we remove 1 5 and get 1. Pause the video and attempt these problems working modulo 5. Now comes the answer. This works not just for 5, in fact we can work modulo any positive number, and it works the same, just with that number instead of 5. Even though this may seem silly, it is actually one of the most used concepts in number theory and algebra. So, what do we call this weird mathematical context that affects how arithmetic works? Well, this is precisely what a mathematician calls a ring. A ring is an arithmetic context. It is a selection of some objects that work like numbers, and ways to add and multiply these objects. For a context to be a ring, however, we need some very special requirements called the ring axioms. The ring axioms are the following. A. Addition. Addition is commutative, that A plus B equals B plus A. 2. Addition is associative, that A plus B in parentheses plus C equals A plus parentheses B plus C, that we don't need parentheses to add many things together. 3. Addition has identity, that there is an element we call 0, such as 0 plus A equals A. 4. Addition has inverse, that for every A there is a B such that A plus B equals 0. We call B minus A. B. Multiplication. 1. Multiplication is associative, that A times B in parentheses times C equals A times parentheses B times C. 2. Multiplication has identity, that there is an element we call 1, such that 1 times A equals A. C. Distributivity. 1. Left distributivity, that A times B plus C in parentheses equals A times B plus A times C. 2. Right distributivity, that A plus B in parentheses times C equals A times C plus B times C. These are all ring axioms. If a set and a multiplication and an addition together satisfy all of these, then we call it a ring. Further, whenever we have a ring, we can take all these rules for granted and use them however we like. Further, we say a ring is a commutative ring when multiplication is commutative, that is that A times B equals B times A. When this is satisfied, the two distributivity rules collapse into a single rule. The first example of a ring we will start with is the ring Z, which has all the integers as elements and normal integer addition and multiplication. This is a commutative ring, like most of the examples we will give. Pause the video, go ahead and go through all the ring axioms and convince yourself that they all hold for the ring of integers. The next example of a ring is the ring of rational numbers called Q, which has all the rational numbers as elements and again normal fraction addition and multiplication. We draw an arrow from Z to Q to visualize that Z is a subring of Q, which is to say that all the elements of Z are in Q and that addition and multiplication in Q of the elements that are also in Z work the same as it would in Z. From here there are many examples we could do. Perhaps the most well known is the ring of real numbers, R, which contains all the real numbers. Again, Q is clearly a subring of R. The next ring is the ring of complex numbers, which we call C and contains all the complex numbers. Between Q and C are the algebraic numbers, which are all the numbers that arise as zeros of polynomials with rational coefficients. This ring we call Q bar. Also, another direction we may take from Q is to the p-adic numbers, which we call QP. See my previous video for more on these. The system we started with, the modulo 5 context, is also a ring, called set mod 5. In general, we get set mod n where n is some positive number. It is tempting to say that these are subrings of set, since their elements are all integers, but these are in fact not subrings since addition and multiplication wrap around and thus work differently than in set. These are hence a sort of standalone set of rings. All the rings so far have been commutative, but we are about to encounter a ring which is not. That ring is the ring of real 3x3 matrices called M3R. This is not commutative because the matrix AB is not always equal to BA. Of course, we could use any other positive integer other than 3. Also, instead of real numbers, we could use rational numbers, integers, or complex numbers. In fact, we could use any ring, and we will get a ring of matrices with entries in that ring. These are subrings of each other in the same way that the entry rings are subrings of each other. In fact, other than matrices, there are many ways we can create new rings from old ones. Another way are the polynomial rings, which is the ring of polynomials with coefficients in some set ring. For example, integral polynomials or rational polynomials. We call these rings R extended by x, where R is the ring we take the elements from. This is a commutative ring, and R is a subring of Rx. Another way is the Cartesian product, which takes two rings, R and S, and creates a new one called R times S. This is the ring of pairs of one element from R and one element from S, and addition and multiplication is done pairwise. We have seen an extensive list of examples of rings, and now we will explore how they are interconnected, further than just subring relations. A homomorphism, which we will call F, from a ring R to another ring S is a sort of connection. It is a machine taking each element from R and mapping it to some other element in S. Each element x in R gets assigned an element in S called f of x. This mapping needs to satisfy some axioms, however. First, the mapping must preserve addition. F of x plus y equals f of x plus f of y. 2. The mapping must preserve multiplication. F of x times y equals f of x times f of y. 3. The mapping must preserve the multiplicative identity. F of 1 must be 1. In a certain sense, these axioms essentially say that f must preserve the structure of the rings. Whenever S is a subring of S, whenever R is a subring of S, there is a homomorphism from R to S that takes each element of R to itself in S. Since subrings must have the same addition and multiplication, the structure is preserved by the homomorphism. 1, like every element, is mapped to itself, so f of 1 equals 1 holds. Another important homomorphism is the identity homomorphism from a ring to itself, which maps every element to itself. This is a homomorphism for similar reasons. Now on to more exotic homomorphisms. There is a homomorphism from the complex numbers back to itself that maps a complex number to its conjugate. I will leave a proof that this is a homomorphism on screen for you to pause and ponder. There is also a homomorphism from set to set mod n that maps each integer to its value modulo n. Note that this exists even though neither is a subring of the other. Another homomorphism is the one that goes from some ring R to the ring of 3x3 matrices M3 of R. This maps R to R times the identity matrix. The final homomorphisms that we will explore go from the polynomial ring R extended by x to R, of which there is one for each element in R. The homomorphism corresponding to the element R takes the polynomial p to p of R, which is an element of R. Finally, we will talk a bit about isomorphisms, which are homomorphisms that are invertible. Essentially, if f is a homomorphism from R to S, then we say that f is an isomorphism if there is another homomorphism g from S to R such as f of g of x equals x and g of f of x equals x. Essentially a two-way structure preserving correspondence. The identity homomorphism is always an isomorphism and it is its own inverse. The homomorphism that takes a complex number to its conjugate is also an isomorphism, and this is as well as its own inverse, as the double conjugate just takes a number back to itself. A more exotic isomorphism is the one from 2 by 2 diagonal matrices with elements in R to the ring R times R. This takes the two diagonal entries to the pair in R times R and opposite in the inverse direction. Whenever there is an isomorphism between two rings R and S, we say that R and S are isomorphic. Isomorphic rings are essentially thought of as the same, as they have exactly the same additive and multiplicative structure, although their elements can look very different. Every ring is isomorphic to itself via the identity isomorphism. We also saw that the subring of M2R that consists of the diagonal matrices is isomorphic to R times R. Now finally we will state an important theorem of rings which we will not prove. Every ring has a subring that is isomorphic to either set or set mod n for some n. Thank you for the attention. I hope you learned something, and leave a comment if you have any questions. Subscribe if you want to see more of this kind of content, and I hope to see you again.